we move now to two newly funded projects in the current CRC, both in Program 2, and the first of those projects is multimodal terrestrial data acquisition and feature extraction, and that will be presented by Jeff West from WA. Thanks, Jeff.
Oh, I'm going to set a timer going on this.
Just listen to the bell.
No, I want to pace myself. Okay, thanks everybody for being here. I won't repeat the title. We spent some time at dinner last night trying to work out a nice acronym, and we sort of failed miserably. So we'll be working on that as part of the project. So I'm leading Project 2.1, and Clive Fraser, of course, is the program chair for that project. And this is that one, right? This is a project which is, I suppose, have recently been thought of in great with great interest in the CRC, because mobile mapping is sort of in the last year or two has suddenly increased in interest around the world. This is a nice little diagram of what we understand by mobile mapping. We have the ubiquitous white van wobbling down the road with some sensors on the roof. It's got GPS, it's got inertial navigation. Many of them have odometry connected directly to the wheels, typically, so they can measure distance. We have, if you look at behind, there's, which is it? That one. That one. Got it. Go back. Right. All these dots where a laser scanner has picked up data on the roads in obviously in 3D coordinates, and you maybe have a camera on the roof, and you're picking up panoramic or omnidirectional data as well. So we have imagery, and we also have laser scanned 3D point cloud type data, typically, all of which is supposed to be geolocated and registered with each other. Over here are some examples of the sort of data you get. This is actually a point cloud that you get from a system by Earthmine, which Clive mentioned this morning, which is being exploited by Langate as one organisation. That's created by Stereo from a NASA algorithm. So this is not a 3D point cloud of the accuracy of a laser scan data, but it's reasonable for some of the things you might want to do with it. This is actually what happens if you take the point cloud data and put it into visualize it. There's the vehicle in the middle, and all this around here is the streets. And you get an idea from this of what you would call an urban corridor of data, because it's not looking straight down. It's not a single image of remotely sensed. It's a large number of images and a large amount of data that's put together to form this rather complicated 3D scene here. This one here is from a laser scan from McMullen Nolan of around Perth, and that's again been put into a visualization system, so you can see that what it looks like, and you get some impression of color as well as distance there. Right. So that's the sort of generic system. The sort of things we want to look at is in terms of applications, because one of the things we need to do is go off and really talk to end users and find out exactly what they wanted from mobile mapping systems. And the big thing is enterprise asset management. So we want to identify and locate street furniture, which can be road signs, lampposts, services, bus shelters, anything that you can think of, which is in the road or transport corridor. We have road geometry, so you've got edges. Centre lines, very important to find. Curbs, things of that nature. We want to do change detection. Oh, sorry, I mentioned power line infrastructure because that's important. Because if they talked about earlier this morning, they talked about looking at power lines from aerial photography. You can't fly aeroplanes down urban canyons without some public concern. So it's but if you can get this sort of thing hopefully from mobile mapping systems as well in cities and things. To do change detection, you need regular data acquisition, which means you have to run this thing every 6 months to a year around the streets or the railways or whatever. But if change detection is quite important. We mustn't discount measurement. Compliance checking is where you have to satisfy things like disabilities, laws and things, find obstructions and things. Road width, curb height, all these things require more accurate measurement than, say, you might get from imagery. So back to laser scanning there. Importantly, all these things lead to fit for purpose. So what we're really talking about here is we want to look at applications and solve those as a fit for purpose, because different organisations have different desires from these types of systems. To give you an example, and this is a picture of Perth, these are the sorts of things we want to do. When we detect things like this, now I'm from computer vision, so I would call this an object although in the spatial industry you probably call that a feature. So a lamppost, drain covers, road widths and things, and basically build databases, GIS layers, whatever, of this sort of information, and with the descriptions. And of course, the issue here is there are so many different features that you're trying to find in these type of street scenes. The question is, how do you do it? Okay, in terms of levels of analysis, and I'll very quickly skip through some of this. There are existing GUIs for manual interpretation and measurement. So EarthMine has one. We've all played with Google Street View, which is mainly just a visualization tool. Cyclone, Polyworks are available for things like 3D point clouds. There are certain GUIs that do semi-automated feature extraction. They can help you find features, which typically you have to manually label. What we really would like to go for is the ultimate goal is fully automated analysis. Now, there are specific methods available from various vendors for certain types of feature, but the question then is, well, that means you've got to have hundreds of different systems for specific features. And what we really like to do is to have a general solution. So that's what we want to try and move towards. Very quickly, a couple of examples of viewers. This is the one that from EarthMine. And this is interesting because it allows you to query an image, say here and here. And because it's got a 3D point cloud behind it from stereo, it can then go and project into the 3D point cloud from that point there, and then try and return you the height of the image from that stereo data. So the image, in this case, the image is just the query method into the 3D data. But of course, it's a human interpreter doing the deciding where to look. This one's quite an old one from Geo3D, and I thought I'd bring this one up because this has actually got patented. The method's got patented just late last year, even though Geo3D's been going since the mid-1990s. Here's an example of sort of semi-automated. This road sign here is picked up by a forward-looking forward-looking laser scanner, which knows approximately how high road signs are, where they exist. But you have to then have a little set of labels here for a human to come along and then label this with what it decides, what the human decides. Now, this is actually, much of this has been automated now, street sign recognition, so that's a sort of low-hanging fruit that we don't need to worry about too much. This was a slide that Clive showed earlier, which is just wanted to show you that there's a lot in this project. This is not necessarily a timeline from this end to this end. Because some of the things like development and utilization applications can come earlier, depending on how complex they are. But it gives you an idea of the research is really in this area. We're not going to do too much on 3D image fusion. That's left up to Project 2.2, but because much of the data we want to look at is already fused and registered by the provider. We're looking at feature recognition for primitives and certain objects. We've got these sorts of things. We want to develop systems to find these sorts of features. Et cetera, some change detection tools. We have to think about the 3D image visualization and storage, because this is a lot of data, and I'll show you that in a moment. And these are the sorts of utilization outputs we want to get from this project. Okay, so very aware of the user requirements for the projects. Give you an idea of the data. There's two data sets here. One is the EarthMine data set, which is we've already Landgate's acquired, and this is an equivalent sort of a made-up set of values or results from looking at if you did the same area by laser scanning. The first CBD, which is not that big, has got 320 kilometres of road, and it was scanned. And it took them 2 days to do that, and we've got nearly 9 terabytes of raw data, because it's basically capturing high-resolution imagery from cameras every 10 metres. And it's taking 8 of those to give 2 panoramas and then generating the 3D point cloud using a stereo algorithm, which of course increases the amount of data, but we've got JPEG compression, which reduces this down. What this means is that this all has to be held in the cloud somewhere on a server, and the only way to interrogate the 3D data at the moment is to do it through the images. So you have to find an image, know where you are, and then you can go and get the 3D data. If I do exactly the same type of scan for a laser scanner with McMullen Nolan specs, 300,000 points per second, I get 8 gigabytes of 3D points. Again, we've got a lot of data, and this is just a small part of Perth. Okay? Lots of data. Oops, wrong one. Okay. Just to show we're not doing anything in isolation, there's lots of areas which are very close to this type of thing. Anyone who's heard of the DARPA's Grand Challenge in the desert, and then the urban one? and you can see the types of vehicles they use. This is actually about controlling vehicles autonomously, and I wouldn't have liked to have been the people driving ordinary cars around when these things were moving about on their own. And if anyone's looked recently at what Google's been up to, because Google's been doing things in this space as well, with some very impressive self-driving cars in California. So there's lots of things in here that can help us in our project. All right, so moving on to the actual research, what it all comes down to, as Clive mentioned this morning, is recognising the features, recognising the objects. Now, I've been in the area of computer vision since I started my PhD in 1978, and it's quite interesting to see how far computer vision has got in this process. And it's getting there, but it's not quite there yet. But given this project is very much focused on what end users want, specific types of objects and situations, we think we might have a handle on how to produce some useful tools out of it. So what general recognition technique, what do we use to recognise? Well, typically you have models, and we can have CAD models and real examples. People are moving towards using lots and lots of real examples, images of real objects, because that captures the variability and allows you to have more general systems, and if you can only get 3D models. What sort of low-level features do we want to extract to measure these objects? Is it colour, texture, shape features, all these types of features? And of course, we're going to do them in 2D imagery as well as 3D point clouds, and we're going to fuse them together or treat them separately. What sort of matching method are we going to use? We're tending towards a machine learning technique, one of which is a thing called random forests, which is what you do if you decide one decision tree is not enough. You have 100 of them, and you do a majority vote. Things of this nature. So these are the sorts of matching methods that we need. We've got other useful information we want to put in. We obviously got a certain amount of information in terms of its location from GPS and orientation from GIS maps. We got other knowledge. We know where a lot of things are at the moment. So these things can be included. And again, we want to try and deal with any object, so we want to have a general solution which is interactive with the user. They can tune it, train it to deal with the objects of interest that they've got. Okay, but that's not to discount this, but we'd rather do general. Okay, so this is the architecture, if you like, that we've been thinking about. This is not that dissimilar from what a lot of computer vision systems tend to look like. But in this case, we've got all this data at the here, 2D images, 3D point clouds from various sources, laser scan data, omnidirectional cameras, stereo algorithms and things like this. And we've got all these a bank of feature extractors. Now, there's been hundreds and hundreds of feature extraction methods generated over the past 30-odd years in computer vision. Most of them have been developed for 2D images, because that's where computer vision really sort of started out from. But there has been work on 3D point clouds, and importantly, there's been work on 3D point cloud feature extraction by colleagues at Curtin through the CRC. Importantly here is that you've got these lines of pathways here which show that in this particular case here, Feature Extractor 2 is working on 2D imagery and the 3D point cloud. So these two in combination is somewhat like Clive talked about this morning about a 3D image, where you've got the imagery and the point cloud data put together. But some of them will only work on 3D, some of them will work 2D. The recognition comes down to, because we've got so much data, 2 minutes, right? Comes down to three separate algorithms, if you like. The enormous amount of data means that what would be really nice to have is a relatively simple search algorithm that finds all the objects of interest, but gives you an enormous amount of false alarm data, and it's a crude detector. So this is a detect objects. This one is, okay, now we've got them, now go and recognise which one they are. And of course, this is going to be working on less data, so this can be more complicated. And the final one, which is very much concerned with the measurement and analysis, is to do some accurate alignment. So we have to look at methods to accurately align models or whatever with the data. And then finally, there's user-defined operations. So this is the allowable increased processing time and complexity. That's the reducing data rate that we hopefully can obtain by having these methods. Very quickly through some features, but I'm not going to go through too many of these because you would have seen some of these before. This is some work we did years ago now, finding ellipses and lines in imagery. So this is some sort of the data we can use. The blue things are ellipses, which are typically circles in the real world. Region growing. on imagery. So this is just this is quite a nice little algorithm. It does not too bad at detecting regions. None of these things are absolutely perfect, and that's the issue. There's no point in spending all your time developing perfect feature recognizers when you can put a lot of slightly duff ones together and still get a good result. In terms of 3D, some of this work is from David Belton, who's in the audience, I think. Yeah, he's up the back there. With the CRC, some very, very good algorithms there for region growing on and picking out, in this case, planar patches, but David's done circles and, cylinders and things. Go away, nearly there. Okay, so there's lots of those algorithms we've got as well. And last thing before the final slide, this is some of the latest things that are going on. I wanted to put this up because I wanted to show you this as an example of where the area is going and where we'd like to look into. This is actually an algorithm that just searches images for objects, and it's not that good. These are actually the best results that you get out of it, but it actually needs a lot of refinement and the inclusion of 3D point clouds because this is on imagery. The red is ground truth. No, the cyan is ground truth. Sorry, and the and you identify. You look at these. You find these objects in images. You use those. You don't do any feature extraction. You tell it to the system to train on all those regions with any features it wants. And then you go and test it on other images. And you'll notice that some of this stuff is quite unstructured. It's found a cow, some cyclists, a bird, aeroplane, cyclist, yeah, cars and things like that. And the idea is that these sorts of algorithms basically cut down your data rate quite a lot. This one is a lot more complicated. It's hierarchical. Again, you train it on cars or people or sofas. And the blue regions in here are showing you the parts that it finds that are these sofas. These are not my algorithms. These are ones that have been published in the last few weeks. So these are the sorts of things we need to basically take and modify to use the imagery and 3D point cloud data. This is the team. There's us at the top, David Belton, Dr. Kwang Ho Ba, Associate Professor Telly Tan, Eric Curtin, 2 PhD students. We talk to all these organisations who are people who want to get hold of all this type of results that we're talking about. Lots of 43PL companies involved. These are companies that generate the data, of course, and many of them under contract from these types of organisations. And importantly, we've also talked to other organisations that aren't in the CRC, but in terms of local government, main roads, people like these. These are the people who would use the information that's generated from the other people. So we have to find out exactly what they want. Okay, so I think I'll stop there. I don't think we need to worry about that too much. I'll put that one up.
Thanks.
All right, thank you.
Thanks, Jeff.